This is Dr. Shankaraiah from Department of Physics. In today's presentation, I will discuss about question bank on Module 5 Nanotechnology, Part A, which is analytical questions. So the first question is calculate the surface area to its volume ratio of a spherical particle of diameter 8 millimeters. So we need to calculate the surface area to volume ratio of a spherical particle with a given diameter of 8 millimeters. So they have given, first we will start with whatever given. So they have given the diameter, which is 8 millimeters. So we are going to convert this into meters. So 8 into 10 power minus 3 meters. So we need to calculate the surface to volume ratio of a spherical particle. Okay. So surface area of a sphere. Surface area of a sphere is 4 pi r square, and volume of a sphere, because here we are taking spherical particles, so volume of a sphere is 4 by 3 pi r cube. So surface area to volume ratio will be surface area to volume ratio is 4 pi r square and volume is 4 by 3 pi r cube. Okay, so that will be 3 by r. So this is the surface to volume ratio of a sphere or spherical particle, right? So now they have given the radius, diameter they have given, we can calculate the radius. So radius is nothing but diameter by 2, right? So that is 8 by 2, so that is 4 into 10 power minus 3 meters. So by substituting this in this equation, 3 by r is 4 into 10 power minus 3. So we will get the surface to volume ratio of the spherical particle, which is 0.75 into 10 power minus 3 per meter. So this is the surface area to volume ratio of a spherical particle of given diameter 8 millimeters. Okay. So r is 4 into 10 power minus 3. So 3 by r. So that is 10 power plus 3. So let us go to the next problem. So the next problem is, if the radius of a sphere made 1/3, how its surface area to volume ratio changes. So they have given that the radius of a sphere is made 1/3. So sphere radius is made r by 3. Okay. So we already calculated surface to volume ratio for a sphere. Surface area to volume ratio of a sphere is 3 by r. But now they have made the radius 1/3. Okay, so now r became 1/3, so that is 3 by r by 3. So that is 9 by r. So how its surface area to volume ratio changes? So we can write this as 3 into 3 by r. So when the radius of a sphere is made 1/3, the surface area to volume ratio increases. Surface area to volume ratio increases by 3 times. Okay. So when radius is made 1/3, surface area to volume ratio increases by 3 times. Okay. So let us go to the next problem. So the third problem is, if the dimension of a cube is doubled, how its surface area to volume ratio varies. If the dimension of a cube is doubled, okay, how its surface area to volume ratio increases. So given the dimension, the size of the length of a cube, okay, so this is cube. So the length of this dimension of each length of each side is doubled. So, okay. So, first let us look at the surface area to volume ratio of a cube. Okay. So, surface area of a cube. Surface, so it became 2a. So, surface area of a cube is surface area of a cube is 6a square, because there are 6 faces and each face is a square. So, area is 6a square. Volume of a cube is a cube. Okay. So, then surface area to volume ratio of a cube. Surface area to volume ratio, right? Volume ratio of a cube will be 6a square divided by a cube. So, that is 6 by a. So, surface area to volume ratio for cube is 6 by a, but now they have mentioned that the size, that length of each side is doubled. So, 6 by, so length of each side is doubled. So, wherever you are going to have a, so you are going to replace by 2a. So, now, so I have here 6 into 2a whole square. So, that is 6 into 4a square. So, that is 24a square. So, surface area will be 24a square and a cube. So, that is 2a cube will be 8a cube. Okay. So, here now, instead of 6a square by a cube, we will have surface area is 24a square divided by 8a cube. Okay. 8. Okay. So, that is 3 by 8. Actually, if you take a cube of dimension a, then the surface area to volume ratio is 6 by 8. Now, because the size of length of each side is doubled, the surface area to volume ratio is decreased by 2 times. Okay. So, instead of 6 by a, we have 2 into, actually, so we should multiply and divide it by 2. So, anyway, so surface area to volume ratio decreases by 2 times. So, this we can write 2 into 3 by a, but there is, So, surface area to volume ratio decreases by 2 times. Okay. So, instead of 6 by a, we just have 3 by a. Okay. So, this we can write multiply and divide by 2. How to understand why it is decreased by 2? So, you can multiply by 2 and divide it by 2. Then what we will have here? 1 by 2 into 6 by 8. Okay. So, that is why it decreased by 2 times. So, when the dimension is doubled, the surface area to volume ratio decreased by 2 times. Okay. So, the next problem, calculate average particle size using X-ray diffraction pattern having 0.1541 nanometer of X-ray wavelength, 0.011 radian of full width and of maximum, and diffraction angle of 45 degrees. Okay. So, we need to calculate the average particle size. Okay. So, first, solution. Whatever they have given, we need to mention first. So, given is X-ray wavelength. So, wavelength lambda is given as 0.1541 nanometers. Okay. So, you can convert into meters. So, 0.1541 into 10 power minus 9 meters, because 1 nanometer is 10 power minus 9. And full width of maximum is 0.011 radian. So, the formula for average particle size is Scherer's formula. It is known as Scherer's formula. Scherer's formula for average particle size. D is K into lambda by B cos theta B. Okay. So, theta also they have given, diffraction angle is given as 45 degrees. Okay. So, K is mostly 1. So, 1 into lambda, lambda is given as 0.1541 into 10 power minus 9. Divided B is 0.011 into cos theta, B is cos theta cos 45 degrees. Okay. So, the answer for average particle size is 1.98 into 10 power minus 8 meters. So, this is the average particle size we'll get for this for this X-ray diffraction pattern having wavelength lambda, and this is the full width of maximum and the diffraction angle. Okay, so let us go to the next problem. A beam of X-rays is incident on an NaCl crystal with lattice spacing 0.282 nanometers. Calculate the wavelength of X-rays if the first order Bragg's reflection takes place at a glancing angle of 8 degree 35 minutes. Okay. Solution. So they have given us lattice spacing. So lattice spacing D is given as 0.282 nanometers. So that is 0.282 into 10 power minus 9 meters. And they have also given us the glancing first order diffraction. So N is equal to 1. And glancing angle or diffraction angle is 8 degrees 35 minutes. Okay. So one can convert this into degrees. 35 minutes we can convert into degrees, because 1 degree is 60 minutes. Okay, so 1 by 35 we can convert this into total degrees. So then we are going to use Bragg's equation, because we need to calculate wavelength. So Bragg's law is 2d sine theta is equal to n into lambda. Okay, so we need to calculate lambda. So lambda is 2d sine theta by n. So n is equal to 1. So lambda is equal to 2. D is given as 0.282 into 10 power minus 9. 2d sine theta is given as 8 degrees 30 minutes, or converted into degrees, because 1 degree is 60 minutes. Okay. So 1 by 35, how much degree you will get? So you can write 8.31 or whatever. So then you will get the wavelength. So the wavelength is 8.419 into 10 power minus 11 meters. Okay. So for this beam of X-rays incident on a nickel crystal spacing given, the wavelength is 8.419 into 10 power minus 11 meters. So let us go to the next problem. So we have used here the Bragg's law, and earlier we have used the Scherrer's formula and surface area to volume ratio of a cube and sphere. Next problem is X-rays of wavelength 1.5418 angstrom are diffracted by 111 planes in a crystal at an angle 30 degrees in the first order. Calculate the interatomic space. Okay. So we need to calculate the interatomic spacing. So they have given us lambda 1.5418 angstrom. So 1 angstrom is 10 power minus 10 meters. So 1.5418 into 10 power minus 10 meters. And they have also given us the angle or diffraction angle theta as 30 degrees, and the order n is equal to 1. We need to calculate D. So I am going to use again Bragg's equation. Bragg's equation or law is 2d sine theta is equal to n lambda. I want D. So n lambda by 2 sine theta. Okay. So substitute n is 1, lambda is given as 1.5418 into 10 power minus 10 divided by 2, sine theta is 30 degrees. So the interatomic spacing is 1.54 into 10 power minus 10 meters. So this is the interatomic spacing for this given X-rays. Okay. Yeah. So let's go to the next problem. So we have used Bragg's equation here also in this problem also. We can use Bragg's equation to calculate various parameters like interatomic spacing, wavelength, and order of diffraction, right? So the next problem is an X-ray beam of wavelength 3 angstrom is diffracted from 100 plane of a cubic crystal. The first order maximum is obtained for a glancing angle of 40 degrees. Determine the space of the reflecting plane and also volume of the units. So they have given us wavelength lambda 3 angstrom. So that is 3 into 10 power minus 10 meters. Then they have also given us the diffraction angle theta of 40 degrees and also first order diffraction. So order is 1. So first we are going to use Bragg's equation. Bragg's equation is 2d sin theta is equal to n lambda. So we need to find the space of the reflecting plane. So we need to find out d. So d is equal to n lambda by 2 sin theta. Okay, so d is equal to n lambda. N is 1. Lambda is given as 3 into 10 power minus 10 meters. 2 sin theta. Theta is given as 40 degrees. So the d will be 2.33 into 10 power minus 10 meters. Then we need to calculate the volume of cubic unit cell. So volume of cubic unit cell is volume of the cubic unit cell is a cube. So yes, so we can calculate AR d cube from this. So yeah, so that is 2.33 into 10 power minus 10 whole cube. Okay, so that is 12.64 into 10 power minus 30 meter cube. Okay, yeah. So once so from this we need. So actually we need A. So we need to calculate A. So here we know only D. So from D, so DHKL is equal to A by square root H square plus K square plus L square. Right? So using this formula, you can calculate A. So A is equal to D into square root H square plus K square plus L square. So that is how we get A. So D we already know. We have calculated 2.33 into 10 power minus 10 and square root H square plus H is so this is 100 plane. So H is 1 square plus 0 square plus 0 square. So that is A is also 2.33 into 10 power minus 10. Okay. So D is actually equal to A because HKL is 100 plane. Okay. Yeah. So the in plane the space of the plane is 2.33 into 10 power minus 10 meters, and the volume of the cube is 12.64 into 10 power minus 30 meter cube. So let's go to the next problem. So here also we've used Bragg's equation first to calculate the interplanar spacing. Once after calculating interplanar spacing, we have used this volume of a cubic unit cell to calculate volume of the cubic unit cell. V is equal to A cube. So we have calculated A from the equation D is interplanar spacing equation. D is equal to A by square root H square plus K square plus L square. So let's go to the next problem, 8th problem. In an X-ray diffraction experiment, peak width at off maximum is 0.6 degrees and its corresponding Bragg's angle is 24 degrees. Calculate the crystallite size using Shankaraiah's equation. The wavelength used in the X-ray diffraction experiment is 1.52 angstroms. Okay. So we need to calculate the crystallite size. Okay. So given is they have given full width of maximum, which is 0.6 degree, that can be converted into radian. Here it will be 0. So 1 degree is 0.017 radian. So by that we can calculate 1 degree is 0.01 radian. 0.6 degrees 0.01 radian, and so this is radians. 1 degree is 0.017 radians. Now I want to calculate 0.6 degrees how many radians. So 0.6 degrees is 0.01 radians. So multiply 0.6 into 0.017, you will get 0.01. Okay. Then they have also given us the Bragg's angle, which is 24 degrees. Theta is 24 degrees. And wavelength also they have given as 1.54 angstrom. So 1.54 into 10 power minus 10 meters. So we need to calculate the crystallized size using Shankaraiah's equation. So that is K lambda by B cos theta B. So K is 1 and lambda is given as 1.54 into 10 power minus 10 divided by B, which is 0.01 into cos theta B is 24 degrees. Okay. So the average crystallite size is 1.68 into 10 power minus 8 meters. Okay. So we have used the Shankaraiah's formula here to calculate the average crystallite size. So let us go to the next problem. So we have used Bragg's equation and we have used Serre's equation. These are the two main equations apart from the surface to volume ratio formulas. So next question, what is the angle at which the third order reflection of X-rays of 0.79 angstroms wavelength can occur in a calcite crystal of 3.04 into 10 power minus 10 centimeters space? We need to calculate the angle. Okay. So given, they have given us the n is equal to third order and wavelength lambda is 0.79 angstrom. So that is 0.79 into 10 power minus 10 meters. And also they have given us the interplanar spacing d, which is 3.04 into 10 power minus 10 centimeters. Okay, so this we can convert into meters. So we 3.04 into 10 power minus 8 and 1 centimeter is 10 power minus 2 meters. So 10 power minus 2 meters. So basically that will be 3.04 into 10 power minus 10 meters. Okay, so now we need to calculate the angle. So we can use the Bragg's equation here. So Bragg's equation, 2d sine theta is equal to n lambda. So we want theta. So sine theta is equal to n lambda by 2d, or theta is equal to sine inverse n lambda by 2. Substitute all the values. So theta is equal to sine inverse, n is 3, lambda is given as 0.79 into 10 power minus 10 by n lambda by 2 into d. d is given as 3.04 into 10 power minus 10. So substituting all the values, we'll get theta as 22 degrees, 22.94 degrees. That is not right in minutes, 22.94 degrees. So this is the angle at which third order reflection occurs in this calcite crystal of the given space. So here also again we have used Bragg's equation to calculate angle. So we can use Bragg's equation to calculate different parameters. For example, wavelength, we can calculate interplanar spacing, we can calculate angle, we can also calculate order. Okay. So let us go to the next problem. So the last problem in module 5. Okay, so the last problem is monochromatic X-rays of wavelength lambda 1.5 at angstrom units are incident on a crystal face having an interplanar spacing of 1.6 angstrom units. Find the highest order for which Bragg's reflection maximum can be seen. Bragg's reflection maximum occurs at an angle of 90 degrees. Okay, so first, given. So they have given us the wavelength 1.5 angstroms, angstrom units are angstroms, 1.5 into 10 power minus 10 meters. And interplanar spacing, d also they have given as 1.6 angstrom. So 1.6 into 10 power minus 10 meters. Bragg's reflection maximum occurs around at theta is equal to 90 degrees. Okay. So we are going to use Bragg's equation, 2d sine theta is equal to n lambda. From this we are going to calculate the highest order n. So n will be 2d sine theta by lambda. Okay, so let us substitute 2d is given as 1.6 into 10 power minus 10 sine theta. Theta is 90 degrees divided by lambda is 1.5 into 10 power minus 10. So we will get rough n as actually 2 point some value, but we are going to approximately take it as second order. So second order diffraction occurs in this for this X-rays of given wavelength and interplanar spacing. So the second order diffraction occurs. Okay. Yeah. So we have solved all the 10 problems in module 5, which is nanotechnology, and then we are going to look at the long answer questions in the next presentation. So these are the textbooks I have used and the references to look at, and to summarize, I have discussed the analytical questions in this presentation, analytical questions on nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.